All right, so 11.4, this is on tree diagrams. So let's see what this tree diagram is all about. So they start us off with what's called the counting principle. It says here, if a first experiment can be performed in m distinct ways, and a second experiment can be performed in n distinct ways, then the two experiments in that specific order can be performed in m times n distinct ways. So let me give you an example. Let's say you had 5 different shirts and I don't know, 6 different pants, and you wanted to figure out how many different outfits can you make? How many different outfits can you make? All right, well, by the counting principle, they tell you that if this is m different ways, that's 5 different shirts, and then n different pants, then what you do to find how many different outfits you can make would be m times n. So it's going to be 5 times 6, which is 30 different outfits with those two, with these 5 and 6 different items of clothing. All right, so that's how it works. Or you can think of toppings if you have 3 different toppings to choose from. And we have, I don't know, 2 different types of bread. Maybe you have thin crust versus deep dish, and then you have maybe you have 2 different sauces. Maybe you have white red tomato sauce and you have a white Alfredo sauce. How many different pizzas can you make? Well, you can do 3 times 2 times 2. 3 for the toppings, 2 for the different types of breads, and then 2 for the different types of sauces. So that would be 3 times 2 is 6. 6 times 2 is 12 different pizzas can be made. All right, so that's assuming that you can only choose one topping, one type of bread, and one type of sauce. That doesn't assume that you can mix things together, which I know that sometimes some pizza places let you do half pepperoni, half olives or whatever. But in this case, we're just assuming that you're only allowed to choose one topping, one type of bread, and one type of sauce. And so there would be 12 different types of pizzas that you could choose from. All right, so that's the counting principle. All you got to do is just multiply, and that will do it. All right, let's move on. So definitions. These are some definitions you want to try to learn. The sample space is a list of all possible outcomes of an experiment. So if you were to list out all the, let's say that the 3 different toppings were pepperoni, olives, and let's just say mushrooms. And then the types of bread were thin crust, and then we'll just call it regular. And then the type of sauces were tomato and Alfredo. So there's 2 different sauces, 2 different types of bread, 3 different toppings. So the sample space would be, there's going to be a lot. There's going to be, you could do pepperoni, thin crust, tomato. You could do pepperoni, thin crust, Alfredo. You could do pepper crust, tomato, pepperoni, regular, Alfredo. Then you can do olives, thin crust, tomato, olives, regular, so on. Basically, you get the idea. You can do that. You can do that, and that. So there are, we said 12 different types of pizzas that you can make. So there's 12, the sample space will have 12 different possible outcomes. So 12 different outcomes, 12 different outcomes. Just to list a couple, you could do pepperoni, thin crust, tomato. You can do mushrooms, regular, Alfredo. Those are just 2 but the list goes on. There's 12 of them. I'll just say etc. All right. Sample point. A sample point is each individual outcome. So this is a sample point. This is a sample point. So there's 12 different sample points. So you can choose any sample point of the
Mr.
12.
Ellis,
Yes.
are you writing?
Yeah.
Because I guess I don't know if my screen or your screen is frozen. Because
Oh.
it's still on counting principle.
Oh, you're still on the first page?
Oh, okay. You just moved it. Okay, there it is.
Oh, that's weird. I wonder why it was so delayed.
Yeah, okay, thanks.
Okay, no problem. So yeah, so there's 12 different outcomes. I only wrote 2 of them, but there's 12 total. And then for a sample point, it's just each of the 12. So it's just one sample point. So I'll just say mushroom, thin crust, and tomato sauce. That's one out. That's a sample point. All right, and then the tree diagram is helpful in determining the sample space. So you want to figure out all the possibilities. So a tree diagram is going to help you find all the possibilities. So let's do a tree diagram. So here's an example. It says selecting ticket winners. A radio station has 2 tickets to give away to a Blake Shelton concert. If held, a contest and narrowed the possible recipients down to 4 people. So there's 4 people total. There is Christine, Mike, Larry, and Phyllis. The names of 2 of these 4 people will be selected at random. So you're only selecting 2 of those 4 to go to the concert, to be the winners of this raffle. And they're being selected from a hat. So it's completely random. And the 2 people selected will be awarded the tickets. All right, so let's see if we can figure out the sample space. So there are 2 tickets that are going to be given out. So 1 or 2 people that are going to be chosen. 1, 2. So how many possible people can be chosen first? How many choices are there to choose for person number 1? There are 4 people that can be winners, right? So that means there's four people that can possibly be the first one selected. First one selected. Oops. So you're drawing people from a hat. So now you take out that name. How many people are left for the second winner?
3.
Yeah, second selected would be 3 people to choose from. And then the counting principle is going to tell you how many different possible outcomes there are. There are 12 different outcomes. All right, so there's 12 different outcomes. So let's write them out. The tree diagram is going to help us. So we're going to use C for Christine, M for Mike, L for Larry, P for Phyllis. All right, so let's see if we can do this. All right, so here we go. So the first person can either be Christine, it can be Mike, it can be Larry, or it can be, oh, Phyllis. All right, so let's just say that Christine got selected. So now that Celine's been selected, now what are the possible outcomes from here? Well, now it would be just Mike can be selected second. So Mike can go second, or Larry can go second, or it always does that. Or Phyllis can go second. All right, what if Mike gets selected first from the hat, then what are the possible outcomes for the second person?
Larry
Larry
and Phyllis.
and Phyllis, or who else? Christine, right? Because
Oh,
what if Mike gets selected first and you can still get Christine second, or Larry second, or Phyllis second? All right, what if Larry gets selected first? Who can be selected second?
Phyllis.
Phyllis or,
Phyllis, Mike, or
Christine and Mike.
yeah, so if Larry gets selected first, then it could be, the second winner could be Christine, Mike, or Phyllis. And then the last one, what if Phyllis gets chosen first, then the possible people for the second selection would be?
Christine, Mike, and Larry.
Christine.
Yeah. Mike and Larry. So there you go. This is first, I'll just call it the first round. And then this is the second round. All right, so if you go, here's one out. So now let's write out the sample space. So the sample space is gonna be, it can be Christine, Mike, CM. It can be Christine, Larry, CL. It can be Christine, Phyllis, CP. It can be Mike, Christine, Mike, Larry, Mike, Phyllis, Larry, Christine, Larry, Mike, Larry, Phyllis, Phyllis, Christine, Phyllis, Mike, Phyllis, Larry. So this is called the sample space, and there should be 12, remember? There should be 12 different outcomes. So let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12. So I'll just write here 12 total outcomes. All right, so that's what the tree diagram will allow you to do. And now you can ask different questions like probability questions. What's the probability that so-and-so will be selected? So let's see. The next slide is going to ask a follow-up question about probability. Oh, it says construct a tree diagram, which we already did. So I put the tree diagram on the wrong side. On this side, they wanted you to do the counting principle. So that was what we did on the previous. It was 4 times 3, which was 12 different outcomes. So I just wrote things on the wrong slide, but you get the idea. So on this slide, I was supposed to do this. On the next slide, I was supposed to do this. All right. So now let's see what the next question is. All right. Determine the probability that Christine is selected. So we need to figure out the probability that Christine is selected. So remember probability, you always want to put the total number of outcomes divided in the denominator, and the numerator would be the number of ways that Christine can be selected. So number of ways Christine can be selected. So if you go back,
First or second.
yeah, it doesn't even matter first or second, as long as she gets selected. So anybody know how many of these have Christine in it?
I think it's 3
You
or
got,
the 4.
here's Christine Zare, Christine Zare, Christine Zare, Christine Zare, Christine Zare, and Christine Zare. So I'm counting 6, right?
Six, yeah.
Yeah, 6 out of
12.
12 total. So it's going to be 6 out of 12, which is, if you divide by 6,
1 half.
1/2. which is 50%, right? 50% chance. So there's a 50% chance that Christine will get selected. So it's a 50-50 chance for her. So that's how this the tree diagram helps you with probability problems, because then you can put the total number in the denominator and then whatever they're asking for in the numerator, and then you just simplify. So let's see if there's another question. Yes, determine the probability that Christine is selected and then Mike is selected. So Christine, then Mike. So we already know that the denominator is 12, right? All right, so anybody know how many ways, how can you do C and then M in that order?
One. The other way is M and C, so it's only one.
Yeah, there's only one, because the other way is MC. That would be Mike first and then Christine, but they want Christine and then Mike. So there's only one way that can happen. So the answer is going to be 1 out of 12. So the answer has to just be 1 out of 12. And that's because it's saying that Christine is selected and then Mike is selected. If they would have just said Christine and Mike are selected, it doesn't matter the order. But the fact that they're saying and then, that means there's a specific order. They want C and then M. So there's only one way that can happen. All right, let's check out the next example. All right, selecting balls with replacement. So the with replacement has makes a difference in the problem. So let's highlight that just because it makes a difference. It says you have 2 balls that are to be selected from a bag that contains 1 red and 1 blue, 1 green, and 1 orange. So there are red, blue, green, and orange. Use the counting principle to determine the number of points in the sample space. All right, so remember we're selecting only 2 of them, right?
Right.
So that means you want 2 of these, call them slots for lack of a better word. Slot. You need 2 slots. So how many choices do you have for the first ball? How many different colors are there? Or how many different balls are there for the first choice? If you reach into the if you reach into the bag, how many
4
different
colors.
how many different marble or balls are there in the bag?
4.
4.
One red, 1 blue, 1 green, 1 orange. So that's 4 different possibilities. So there's 4 different possibilities. And then for the second ball, you're replacing it. See how it says with replacement? So that means you're going to put the ball back into the bag. And for the second choice, how many balls do you have to choose from now?
4.
4.
4, because you're replacing the one that you chose. That's why the with replacement makes a difference. If it says without replacement, what would this be?
3.
It would have been 3 because now there's only 3 balls to choose from. But yes, you're right. So this makes a big difference. So there are going to be a total of 16 different outcomes in your sample space. So this tree is going to be pretty large because it's going to be 16 total. So I have to draw this kind of small. All right, so we'll use R for red, B for blue, G for green, O for orange. All right, so let's try this. They want you to construct a tree diagram so that we can list the sample space. So for the first round, or the first time that you reach in for a ball, you're going to have 4 possibilities: red, blue, green, orange. And then for the second round, because there's replacement, that means what could be the possibilities after you grab a red?
Red, blue, green, orange.
Yeah, it's just going to be the 4 colors all over again, because you can replace the ball back in there. So you can get another red, or you can get a blue, or you can get a green, or you can get an orange. So basically, this is going to be, you're gonna draw that here, you're gonna draw it here, and you're gonna draw it here. So you're just gonna draw this tree diagram 4 times here, here, and here. So if you get a blue ball first, for the second selection can be the same thing, red, blue, green, orange, red, oops, red, whoops, red, blue, green, orange, red, blue, green, orange. And now I just have to draw the lines. Okay, so there's your sample set. So now we have to figure out how many there are. So 1, 2, 3. All right, so we already know. All you have to do is count the leaves. These are called leaves, you know, because this is the tree. The tree has leaves, so these are the leaves. So the first, you can either get a red. So sample space will be red. It'll be red, green. I'm sorry, red, blue. You can get red, green, or red, orange, or you can get blue, red. You can get blue, 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 green, blue, orange, or you can get green, red. So you get the idea. You just go through each of those lines. Green, red, green, blue, green, 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 orange. And lastly, you can get orange, red, orange, blue, orange, green, orange, orange. And if you count all these, how many do you think there's going to be? We should be 16 because we already did that part where it says there's 4 choices for the first selection and there's 4 choices for the second selection. So 4 times 4 is 16. So that's the nice thing about the counting principle. You'll know ahead of time how many outcomes you should expect. So there are 16 different outcomes. And now they're going to ask you probability questions, of course. So let's look at the probability questions that follow. All right. So the first question is, determine the probability that the red ball is selected twice. So the probability that you get red and red. Anybody know what the denominator should be?
Should be 16.
Yeah, very good, because there are 16 possible outcomes. And then how many of them have red and red?
Just one.
Just one. Yeah, the very first one. That's the only one that's RR. So that's the only one. So it's going to be 1 out of 16 probability. You can always convert these to decimals. Some people like to see this in decimal. So if you want to convert it to decimal just to get an idea of what the probability is in decimal form, then you do 1 divided by 16. So 1 divided by 16 is equal to 0.0625 on your calculator. And then if you wanted to convert that to a percentage, remember to go from decimal to percent. You move the decimal 2 spaces to the right because you're multiplying by 100. So that would be 6.25%. So there's really 3 representations for probability. It can be written as a fraction, as a decimal, or as a percent. So in this case, it doesn't really tell you what they want. So you can just leave it as a fraction. But I think it's easier to to think about in terms of percentages, because we know that 100% is certain, 0% is impossible. So 6% is it's a very low percent, right? So if you're a betting person, you would probably not want to bet too much money that it's going to land on, or that you're going to get two reds, because the probability is very low. All right, let's look at the next question. Determine the probability that neither ball selected is orange. So the probability that the first one is not orange and the second one is also not orange. So we already know the denominator is 16. So now let's think about, see if you can figure out that neither ball is orange. So anybody know what you would do in order to find out that out?
It's 8. You would count all the probabilities that don't have orange in it.
Exactly right. You just look at all the outcomes that don't have O in it, or orange.
So
So
nine.
let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9.
Nine.
You are right, 9. So 9 of them do not have an O. So that means that the answer would be 9 out of 16. And we can, no, you can't simplify that. Let's convert it to a decimal just to get an idea if that's a high probability or a low probability. So on your calculators, do 9 divided by 16. What do you get? I am getting 0.5625, which if you convert to a decimal, that means you're going to move the decimal percent, you're going to move it 2 spaces to the right, which would be 56.25%.
5%.
So would you say that the chances are good or not good that you'll get something that does not have an orange?
Somewhat.
Yeah, it's a little bit better than half, like a 50% chance. It's higher than a 50% chance. 56 is higher than 50, obviously. So yeah, if I were betting, I would say yes, I would bet on this because it's higher than 50%. All right, so that's how you do that. Let's look at the next question. Determine the probability that the orange ball is selected at least once. So, okay. So probability that O is selected at least once. So how would you determine that? We already know the denominator is 16. So now we go back to see at how many. Yeah, so how would you figure out the number of ways that you can get at least one orange?
Six.
Anybody else think that's right, or what do you guys think? What was your strategy, or what was your approach,
Oh,
Erica?
I'm sorry. No, it's 1 because at least one orange, right? Or
At least,
is it 6 because each one has an O and it's only one O?
it can be at least one, so it can be one or more. So one,
Oh,
or,
so
yeah, one.
7.
Yeah, you're right. So this one has at least one. This
Oh,
one,
okay.
this one has at least one. This one, this one, this one, this one, and this one. That one has at least one. So it is 7, right?
7.
Yeah, it is 7. So that's what that problem that's what that would mean, 7 out of 16. And let's just find the probability. 7 out of 16 is equal to,
0.4375.
yeah, in percent, 43.75.
75.
Yeah, so that's a little bit less than 50% chance of happening. All right. So that's what the word at least means. There is another way to do this problem. Whenever you see this key phrase at least once, there's a kind of a shortcut. The shortcut is the probability of at least, oh, I didn't write that right, at least 1 is always equal to 1 minus the probability that none. So this is just a formula that you can use whenever you see the phrase at least 1. You can always find the probability of at least 1 is always equal to 1 minus none. So let's see if we can do it this way, just to see if we get the same answer. So what's the probability that you get 0 oranges? 0
One.
orange. Let's see, 0 oranges. How many of these have 0 oranges?
Oh, 7. Oh, wait, I'm wrong.
Wasn't it 9?
I think it's 9.
I think you're right.
Yeah, it is, right. The
That's
9.
9.
Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are, so it's 9 out of 16. So that would be the probability that none of them have an orange. So it's going to be 1 minus 9 out of 16. That's a probability of at least 1 orange. All right, but here's another way to write 1. If you want to get clever, another way to write 1 is 16 over 16. Do you guys agree that 16 over 16 is the same thing as 1?
Yeah. Yes.
All right, so you can just say 16 over 16 minus 9 over 16 is, what's 16 take away 9?
7.
7.
Yeah, and look at that, you get the same answer. So you do get the same answer.
That's good.
So there's 2 ways to do it. Sometimes in probability, this question is really difficult to find directly. So what people do is they'll use a formula because sometimes this is easy, but this is hard. So it's just a kind of way to work around the difficult problem and do it in an easier way. Sometimes, in this case, it wasn't that hard to find this directly, so we were able to do it, but sometimes it's not so easy. All right, let's look at the next problem. Oh, and there it is. The same thing I just went over. The probability of an event happening at least 1, that's the key phrase, is always going to be equal to 1 minus the probability that the event does not happen. So that's what we did. So here's an example. For example, if you are planting flowers, suppose that the probability of not getting any red flowers from the seeds that are planted is 2 out of 7. Then the probability of getting at least 1 red flower is 1 minus 2 over 7, which is 5/7. So they're just kind of showing you an example of how to apply this formula. All right, so the probability of not getting flowers is 2 out of 7. So the probability of getting at least 1 red flower is going to be 1 minus 2 out of 7. And then another way to write 1 is 7 over 7, right? That's the same thing as 1. So instead of writing 1, you can just change it to 7 over 7 so that you can subtract easier. So 7 take away 2 is 5.
5 over 7.
Yeah, and that's exactly what the answer is that they got. So that's how it works. That is pretty much it. We are done. So
That fast?
yeah, it was a short lesson. It was a short lesson today. Very short, which I do kind of have to leave a little early today. Did you guys want some time to work on the homework? Or did you guys want to just kind of call it a short day?